I was even in time.
Before we start the session with the three lectures this morning, I would like to say that the organizing committee was really impressed from your work and your presentations yesterday. So we have, let's say, decided to give you, let's say, an offer. We have students, let's say, scientific magazine, where students from all around Europe, all around the world are able to submit their work. And it is following the exact process of the scientific review of usually the journals, the scientific journals are doing. It's called Open Schools Journal for Open Science, promoting the idea of scientific, let's say, research that is also taking place at the school level. So it's a magazine, a scientific magazine designed exactly for the students. So we will share with you the guidelines in order to prepare a paper. You can submit your paper to this journal, and then you can see it published. This is documented, let's say, under the specific system of scientific journals. You will receive a DOI, and you can use this also for your CV later. Not only, let's say, having a participation or the presentation in a summer school like this, but also to have a publication of your work. So stay tuned. We will share with you the guidelines, and if you want, you can submit your work to this journal. So now we will go to our program. Clearly, there are a number of, let's say, demanding issues that we are dealing here with quantum physics and quantum mechanics. And it's really important to see how this can be really integrated in issues related to everyday life. So today we will have the chance to see some, let's say, cases that are bringing us closer to the applications of quantum mechanics. The first talk is from Professor Goran Georgievich from the University of Nice. He is the ex-president of the Balkan Physical Union. And I have to say, from my experience, I'm working, let's say, here in the field, and I'm working also with him for many years. If I want to, let's say, describe a person that has a vision for the development of Balkan scientific community, is clearly Professor Georgievich. So it's my honor to give the floor to Professor Georgievich. Let me open the presentation also for a moment. So the floor is yours.
Thank you. So, first of all, thank you, Sophocles, for a nice introduction. I'm very pleased about that, and I can say honestly that after the confidence of 9 years, I think you are right. Okay. I was not able to come the previous year, so this year I'm here. Thank you, Kostas, for invitation and the local organization. Thank you, Sophocles and his team for also make it possible. Thank you for the colleagues from Thessaloniki and Hellenic Physical Society. And I'm very pleased that I see that this time we have the students, it's you and your professors and teachers here in Thessaloniki, plus a lot of students from Greece. It's very nice. And maybe if I will have time, I will speak a little bit at the end of my talk about something that Sophocles mentioned about the physical community. Okay, I will, when I go, then I will talk a little bit louder. No, I think it's okay. Do you hear me well from this position? No? Ah, for the live stream. Okay. Yeah, maybe it's good. I respect all the audience, but I give some preference to the people who are here inside. Okay. So, the reason that I accepted to give a talk and to choose, it's okay? And to choose this topic, I think it's related that I taught subject physics of the microworld since from 2006 to 2011 at a grammar school in Niš in Serbia. It was the unique program and unique curricular class for the pupils age 15 to 19, 4-year program, for pupils interested in sciences. By some administration reasons, it was called a class for the gifted pupils in physics, but in fact it was not. And on the 4th class, it means age 18, 19, we introduced physics of the microworld, and I taught for 4 years 3 topics. It was quantum mechanics, it was nuclear physics, and it was particle physics. As you can imagine, it's not easy at the age of 18 to teach that. So I had to pass through the literature and to invent something so that it can be present at that age. Because you are younger here, most of you are younger, I will go a little bit, I think, more basic, and I hope that my lecture will be one of the least complicated, do not say the simplest one, and I would be happy if we would communicate during the lecture, because I put also some topics here. As Sophocles told, I'm full professor in theoretical physics at University of Niš in Serbia, and also I work and I'm executive director of the Southeast European Network in Theoretical and Mathematical Physics, which was established in 2003. And we did, beside the theoretical and mathematical physics, also partially with Sophocles, with Kostas, we did also some program on physics education for teachers and students. Let me start. So, why we need quantum physics? I think there were, and there are, a lot of answers, but I didn't see so much. Maybe I missed some of lectures here, but I didn't see that there were accent when and where we need quantum physics. Do we need quantum physics for everything? I will try to offer you some answer to these questions. So we are now in the International Year of Quantum Science and Technology. United Nations organize almost every year a few international years of something. Here are a few that I selected that are related to the science and technology. As you can see, it was International Year of Chemistry, etc., etc. In 2009, if I remember well, was the International Year of Astronomy. In 2005, it was International Year of Physics. So here we give also a small contribution to the international program, to the world program of the quantum science and technology. Because now I'm 60-something, I can tell you that during my life, from when I was a student till now, when I was a student there was just a bit about some quantum technology. But in these 40 years, it's a huge progress was done, really, and we will see how it will be developed in the future. So it means that quantum mechanics, that even now for some people is something like a miracle, like a dream, nothing understood. Our civilization is able now somehow to ride on the quantum waves and to control it. I think it's a huge, and for me, a little bit surprising success. I have planned to speak a little bit about formulation of classical mechanics in a sense that it can be transferred to quantum mechanics, but I gave up of that. Instead of that, I will just mention some point which can connect classical and quantum mechanics, but I speak more about the units, about the dimensional analysis, about the power of the units, because I need it and I think it will be useful for you to understand when and where we need quantum mechanics. I will mention the Schrödinger equation, harmonic oscillator as a standard example. And in the end, I will offer you something related to the visualization of quantum physics, a fantastic book that was published like 20 years ago. And I would recommend to many teachers, first of all, but also many students to have a contact with this book. And finally, I will just a little bit mention what is beyond quantum mechanics and about quantum gravity and some things that I started my scientific career like 30 years ago, which is related to the so-called Planck scale physics that I will explain what is it. Maybe some of you know that. So, first, well, when or where we need quantum mechanics? Many physicists, even experienced one, will offer an answer as when we use quantum mechanics. Is there anybody of you who would tell me when we use quantum mechanics? Please. What means microcosmos? Why on atom scale? Why is not on the, let's say, super molecular scale? Yeah, but, okay, this is the standard answer. I mean, there is something like that, where we are dealing with the small particles as atoms or molecules, let's say, of the range 10 minus n to 10 minus 10. It's okay? Okay, this is one of the more standard answers. The second, less frequent, is that we are dealing with the light particles, let's say 10 minus 25 to 10 minus 30 kilograms. It means atoms, we mean about the protons in the core of the atom, or electrons, which is about 10 minus 30 kilograms. But still, it's not quite clear why exactly at that scale. And is there any border? What if there are macromolecules? What the macromolecules or atoms are very fast, have a lot of energy, or are very slow, or can be almost to the zero temperature? That's also an interesting question, which usually skip to start first as soon as possible to do experiments or to do formalism, because formalism in quantum mechanics is not easy. That's true. So I said, there is no reason for these specific values, for distance. Why? Why 10 minus 10 meters? Why this mass? And to offer you an alternative or well-known answer, but usually do not go to the high school pupils, what I think is wrong, I have to introduce a physical value, action. And in fact, action is one of the most important value in physics, quantity in the physics. What is action? So dimensionally, it is a physical quantity which can be represented as energy times time. So you have some energy that is invested or spent or whatever during a time. That means action. For instance, if I'm jumping 1 second, that's some action, that's some energy. If I'm jumping 10 seconds, that will be 10 times more energy, etc. Why it is important? In the same time, the same dimensionality has angular momentum. I'm pretty sure you are familiar with that. This is the vector multiplication of the position and the momentum of a particle, or momentum of inertia times frequency. Why it's also important? I think even you know about the spin of the particles. There are something that particles like rotate, not exactly, but they have some inertial, inside they have something like a rotate, okay? But when you start to learn physics, more or less, the first one you use international system of units, mass in kilogram, distance in meter, time in seconds. Why? Because it's useful for us. It's a history, how it was done. You know, there in the Anglo-Saxon countries, there were some pounds, I don't know, yard, etc., etc. Now there is an international. Even you can be punished if you do not use these units. So this is because we are told about between 1 and 2 meters. Things around us that we use every day are about this size. Distance, standard distance we are around us, it's like a half a meter, 1 meter, 2 meters, 5 meters, etc., etc. So that's also useful. And time unit, second, is something that we can really observe until 0.1 or 0.2. I think the reaction is about 0.2. What we can react if something triggers us is about that. So 1 second looks like a normal time. But our nature, our universe around us have to use exactly these units. And how to know what should be something like a standard or normal or natural physical length, physical mass, and physical time. We do it measuring some physical values that exist independently of us. Speed of light in the vacuum is, you know very well, 3 times 10 power 8 meters per second. Pretty big one. Universal gravitational constant, it makes us that we have to jump and to use some force to jump 1 meter or to lift some things, etc. It is related to this. Of course, it's a huge mistake, sorry. 10 minus 11 Newton meter per kilogram, isn't it? Sorry, when I did it, I used this copy, etc. So gravitation is pretty weak. In the SE system, it is 10 minus 11. Gravitation is weak. Remember, in the column below, you have this constant of interaction, which is about 10 power 10. 10 minus 20, 21 times more than it. And I think there was a lot of things here done. Maybe you saw how to measure Planck constant, etc. This is something before 10 minus 34 joule seconds or kilograms per second square. It's very low. Okay? So it means that universe has something different as natural units. What is length, mass, energy, action, and whatever. Something that might be you know, might be you do not know. For sure, you can find easily on the internet, because now almost everything can be found. But I challenge you to find what would be, for instance, Planck temperature. What was the temperature we believe, and there are strong reasons to believe, that when universe was born, the temperature of this proto-universe was something. And you can calculate that using these constants. It means Planck constant, this is with slash, gravitational constant, Newton constant for gravitational interaction, and speed of light. How to do that? You took any unit you want, and then make the measure analysis. So you know H is in joules second. So you know this is in the joule second or kilogram meter square. And then you solve this equation. So for instance, let's try to find what would be the length which is related to the fundamental constants we observe, we can measure in the universe. So Planck length is 10 minus 35 meters. Very short. To remind you, the core of the kernel of the atom is about 10 minus 15 meters. So it's 20 times less than the kernel. It's like a new universe. 1020, and 1020 more than atom would be 10 power 5 or 10 meters. It's a huge. Planck time. Again, you solve this equation. You got here 10 minus 44 seconds. The shortest, as I know, the shortest quantum effect that I know, it is the life of some resonance, some kind of particles made by quarks. This is about 10 minus 22, 10 minus 23 seconds. Still 10, 20 times less. Planck mass, surprisingly, Planck mass is a huge, 10 minus 8 kilograms. Because mass of the electron is 10 minus 30, mass of the proton is 10 minus 25. And you can calculate Planck energy. It's simple. You just multiply it with the velocity of light, and you will get 10 power 19 giga electron volts. It's a huge energy. It's an energy of mosquito. You will say, okay, but how it can be? But yeah, but mosquito has a mass of about 10 minus, I don't know, 1 gram, and some kind of the velocity. So imagine that something like an electron has energy as a mosquito. So I challenge you, using Boltzmann constant, to find other Planck units. And I think you will, for instance, what would be the density of the proto-universe? How much matter should be dense in the beginning? The temperature, etc., etc. So now people will say, okay, how it's connected to the quantum mechanics? So I think most of you see this equation, and I think most of you do not have idea what is it. And when you learn differentiation, this calculus, then you will know to calculate that, etc., etc. And maybe you will understand, okay, how Schrödinger came to that idea. I know something how Schrödinger came to that idea. Maybe Sophocles knows a bit more than me, but it will something to discuss among the friends. It's not a scientific point. But let me offer you something like an alternative alternative way to come to something like a Schrödinger equation. What is here? Who will tell me what is written here? Please. Can you a bit loud?
Mechanical energy?
Kinetic energy plus potential energy.
Yeah.
In total mechanical energy.
Yeah.
Okay. This is momentum. This is mass time velocity. And I write now this in this way, which is maybe more better known than with the momentum. Okay. So there are something very important, the total energy, and usually the total energy is conserved. Is there any of you have idea or read or heard when the energy is, when and why energy is conserved? Yes, please. Sophia is on the wrong place in the right moment.
You asked why the energy is conserved.
Yes. Why or when or both? Yes.
Okay. So, energy is conserved in general when there's no friction, basically. So, the total energy is stable. It does not change.
Let me ask you something. Let's say that you have the same diet every day and you go to the beach to swim.
Yes.
You will swim every day, or you will be dressed every day, or it changes from time to time? It depends on the weather.
Yes, it depends.
And the weather depends of several things. One of them is the position of Earth and of the Sun.
Certainly.
Okay. But in principle, the energy of the movement inside the sun system, or solar system, etc., is more or less conserved.
Yes.
So, at a bit next level, maybe it can be even presented in a much simpler way, but I didn't that. So I will tell you that the energy is conserved when when the time is homogeneous. So where there are no difference between momentum. For instance, we do the experiments, and we can do experiments, most of the experiments in the morning, in the afternoon, in the evening, etc., because it's not relevant. All time moments are the same. So it means that energy is conserved in a system when time is homogeneous. Of course, what you told is true, but you speak now about non-isolated systems. But even in the isolated systems, if the time would be not homogeneous, we would have something else. The same reason or the same techniques can be used for the law of the conservation of the momenta and angular momenta. This is related with the homogeneity of the space and isotropy of the space. It means that any direction is equivalent to any other. Okay? So, you heard that we need wave function. Why we need wave function, I will try to present you a little bit later, but I think you see there are some kind of the wave function. What is the wave function? Roughly speaking, it is a replacement of the vector of the position. So in classical mechanics, we try and we use vector of the position, and calculating the changes of the trajectory, we know about this particle or this system. In quantum physics, we need a wave function, and wave function is something that we can use to describe the system. So, Schrödinger equation in principle is nothing else than putting wave function in a special way in this conservation of the energy. Schrödinger equation of motion, I prefer to, in particular, to talk to younger students, to pupils and students beginners. The Schrödinger equation is one form of the law of the conservation of the energy. So technically, it comes to this first equation when you transform kinetic energy instead of function or a number to an operator, potential energy to a operator, and total energy as an operator. And then when you got this form, you will exactly got it. What is operator? I came just maybe half an hour before to explain you what is operator and what is the wave function. Is there any QR code around? I think you have in this program you have QR code. You have here this QR code. Okay. You use your phones. You know that better than me. You open your camera. You put it on there, and you read the website, the organizers, the committee. In the restaurant, you can read the menu, what is on etc., etc. So, maybe people did it before me, but I never heard it, so it's not a. So, you as a generation of the digital generation, or whatever, the wave function is a kind of QR code that nature provides to us. Till Schrödinger and his inspiration and other guys, we didn't know there is something like a wave function, to imagine something like wave as a QR code. And these operators are the mobile phone's camera that you can get information. What is the momentum of the wave function associated to this particle? What is the potential energy to that? What is the total energy to that, etc.? What is the angular momentum, so-called spin, etc.? So, in a sense, wave function is a kind of QR code that the nature attach to the electron, to the positron, to other particles that we use wave function. And this classical quantity as momentum, velocity, kinetic, potential energy, in quantum mechanics are transformed to the operators to that. Still, I didn't answer when and where we need quantum mechanics. Okay, let us come back. So, you know that Planck constant, which was measured at the beginning of the 20th century, has a very, very small value. Why we need at all Planck constant? We need because Planck explained, I think many people know that, and there was two problems how to explain and calculate the black body radiation on the high temperature, on the small temperature, on the long distances. You know that was a disaster. And then Planck said, no, radiation cannot be emitted in the quantity you want. Nature ordered that it can be only the frequency time this teeny constant, Planck constant. It is 10 minus 34. Okay, let us see what is the action attached to us in everyday life. So, if someone is about 50 kilograms and it walks like 1 meter per second, etc., it should be like 25 joule second if he move for 1 second. Let's take a micro oscillator with a mass about 1 gram and maximal amplitude, elongation to be 1 millimeter, and with a frequency 1 per second, the action will be 10 minus 9 joule seconds. Okay, it is much less than in this case, but still 25 orders bigger than the Planck constant. Let us go to the electron in the hydrogen ground state. The mass of electron is about 10 minus 30. Velocity is about 1 million or 2 millions meter per second. And usually, distance is about 10 minus 10 meters. So this is about 10 minus 34 joule seconds. This is the same order as the Planck constant. You can calculate yourself if you go to the kinetic energy time 1 rotation of the electron around that. You will get more or less the same result. So, what I wanted to tell you, it is that quantum mechanics has to be applied when system has an energy, action, or angular momentum related or the same at the Planck constant. It's not necessary to be at the level of the atoms and molecules, usually it is, but in principle is not because this is specific for that. It is because the angular momentum and action energy at that level is exactly on that Planck constant. Why Planck constant has this value, we don't know. This is something that's related with how our universe is done and on the basis of the laws that are valid in our universe today. And just to trigger you, in particular you who will maybe continue to do physics, or even if you do not physics, one of the most important law we know, it is the principle of the least action, of the minimal action. So, why particle goes like that? For instance, if I put it down, why it goes down? If I throw out, why this is this trajectory? These trajectories, in the classical case, it is because during this trajectory, this action is a minimal one. And for that, we got the whole action. In the quantum mechanics, something is similar. The probability for a particle to move, to have evaluation like that, is the maximal at the classical trajectory. Okay? What I took from other authors. So, this is as a colleague told, harmonic oscillator. We have a string here, we stretch it. We have a mass, there is no friction. We know Hooke's law, the force that is on this body here is related to the constant, which depends on the quality of the features of this spring and how much we extend it. Okay? Harmonic oscillator, I think you know this equation. If you don't know, it doesn't matter. So, when we solve it, we go a sinusoid. So, A is an amplitude, here is a mass, here is the constant, and this is the time. So, we have a sinusoidal evolution of the presentation of the trajectory of this particle. This is a classical case. We can present it in a different way. Namely, this is the force, but this force is a potential, so we can equivalently discuss this case as a particle, means this body here, mass, that instead of linear, that it is like a pendulum, let's say, or the particle that goes up and down, up and down. This is coming from the 0 point, let's say, 0 position. Here is some mathematics, differentiation, integration, whatever, but this is done in the same way. What we see? We see that this particle can maximally elongate until amplitude A and cannot go out of that. Energy of oscillator is here. Classical turning point, you can calculate if you want action, etc. Doesn't matter. Classical particle can never go out of that. And in the quantum case, it's interesting that particle can go out of this. But what is more important? Here, the potential energy would be zero. When the spring, when the oscillator goes through the zero position, the harmonic oscillator has a potential energy, you can see here, zero. But in the quantum case, it's interesting that because there is uncertainty, we cannot know exactly where is the particle and what is the momentum at that. We find that the zero energy, not zero energy, the zero state, the stable state, has an energy different than zero. This is one of the effects we have in quantum mechanics. And usually when we want to understand something and to make a parallel difference between classical and quantum, we do in that way. There is a book that I would like to recommend to you. This book is here, and now I will present it on the... So the name is Visual Quantum Mechanics. It's written by Professor Bernd Thaler, I think professor at the University of Graz. I had the privilege to meet him in Munich, to talk to him. This book got I think, annual award of the European Academy of Science. And this is the visualization of the quantum phenomena through the wave function. And in a few minutes, I will show you some of this visualization. For instance, did you have here, Kostas, did you have during the school mentioning or presentation of the double slit experiment? Yes. Okay, so you know, we know from the beginning of 19th century Young experiment, when we know that particles are the wave structure, because there are interference of the light. But there was a huge discovery that electrons, even one electron, have the same wave structure, because it seems that electrons, it looks that electron interfere with himself and make this structure here. So let me try to show you some of the presentation, visualization of Professor Bernd Thaler. I think I need a help to find the stick, Costa. Please come here. To find the stick, where is the stick on this? I opened something. Here. No, it's not. Yeah, visual. Thanks a lot. Sorry. Because I was not able to find. Okay, thank you. Sorry. So focus, it does not work now.
Which number do you need?
I don't know why it does not open.
Just a moment.
Opening? In the background. Yeah, but this is in Greek. I don't know what is to open with.
Maybe είναι ανοιχτό ήδη. Είναι ανοιχτό ήδη. It is open already. It was open already.
Yeah, but how to see? I know you're a little bit tired, but please try to focus to understand what is here. So this is like it is like a wave. Let's say you have a wave which comes from one to another wall. Okay, but in this case, it should represent a quantum particle, like one electron, which move from one to another, let's say, wall or some potential barrier, some electric wall by the voltage, let's say. This is a, let's say, free particle. This is, the wave function looks like a free particle. And then colors you have here. This is distribution of the momentum. Distribution of the frequency, because every particle is combination of a lot of waves inside. This is interpretation that offers wave function of the quantum mechanics. Okay? So I hope that I will succeed with the next one. Double slit experiment, which is a very fundamental, maybe one of the most fundamental in physics. It's not clear where it is now.
Let me.
Aha. Okay, thanks. Just to recognize icon. So this is a visualization how we could try to visualize, to imagine what happens when an electron, let's say, as a combination of the waves inside, pass through one slit. How to kill it?
Just click outside.
Uh-huh.
And this
Good.
appears. And then you're back here.
Because of my computer, it does not work. I prefer to have a mouse. Okay, so I hope there is another one. Good.
I don't think that we have another.
No?
It's not a USB. So we can remove this one.
but-
It will not play the
Okay,
laser.
I understand. Thank you. Okay, so I think the next one should be here. 16B. This is most or less the same. Let's go further. 17, nah. 17. So here. So the interpretation we can get from the calculation of the wave function is that a compact particle, let's say one electron, can be understood as, I hope, stop. So, electron is electron, and we can know something about it, but when it interacts, the whole physics is based on our exploration of interaction. In principle, as a person, you don't know who is who and how he reacts until he's in a situation to play the basketball or dance or solve the problem or whatever you want. So, one compact particle is still a compact particle, but we detect something that this particle is disintegrated in the infinitely many of the waves with a different frequency, and because of that we have the same factor with the light. At that point, light and electron are very similar. And when it passes, we can say that there are interaction between the waves which are in this QR code inside the electron, and then continue, and then we have the image we have here that I show to you. Here. This is a visualization how to understand that one electron can give this picture we have for the light. When we have a lot of photons, they interact and then make this diffraction image on that. So I think I'm perfectly in time. I would like to thank you very much. And just before you, sorry. I go to the end, so that's the reason why I lost my presentation. I would like to say something about the Balkan community, and etc., etc. So, of course, I'm very happy to be here. But beyond physics, or we are people, we are young, we are older, but to belong to a community is a great thing, and to know people who are a bit different than you, but they make all us rich. So I'm very pleased to come here, and as here it is a flag of Greek and Serbia at some certain place because of some certain reasons. I think that all we here give a bit more or a bit less contribution to have in the Balkan Physical Union 10 flags, and tomorrow there will be a lot of more flags of our neighbors from, not from the Balkan, from other sides, and to have as much as possible to have a fruitful and really full life of the exploration on the challenges that we will try to fulfill and to enjoy it. So I tried a little bit to contribute to that. I tried also to do something for your older colleagues, for the PhD students and colleagues, but that's another story. So thank you again. If there are some questions, I will be happy to answer, and I hope that you get some ideas for the future. And if I can say 2 words more, I missed to tell you about beyond quantum mechanics and quantum gravity. So, is the quantum mechanics the last theory? No. When we can apply it? We know we apply it when the action is about the Planck scale. The quantum mechanics we use is a slow quantum mechanics. It's for the particles that move reasonably slow. Reasonably means 1 million meters per second. but the speed of velocity is 300 millions of the meter in seconds. So the next horizon will be around the Planck scale, not 10 minus 10 meters, then around 10 minus 35 meters. Not the physics phenomena that takes 10 minus 10, 10 minus 15 seconds, that will be about 10 minus 44 seconds. So, what is this? This is when the Planck length became a black hole horizon. Let me spend 30 seconds. So, do you know how we measure the distance? We measure the distance by meter, isn't it? But with the electronic microscope, we put the light more and more, with more and more energy, to locate, to see a small particle. When we add more and more, there will be a limit. The limit is 10 minus 35 meters. To see in principle, to see something 10 minus 30 meters, you have to put energy to the photon 10 power 19 GeV, giga electron volts, or 10 power 9 joules. So at that moment, you put so much energy that you make a black hole. So this is the limit of the physics based on our knowledge. At that situation, imagine so much energy, so much mass inside. We have that gravity and the other reactions like electromagnetic reactions, nuclear interactions, etc. are the same. In that case, we believe that space will be discrete and that we will have the ultrametric geometry. So what is ultrametric geometry? You have something like a defragmentation of the space in the points which are point-like but completely different structure. So there are something similar in physics we call fractals. So this is the next horizon that we will maybe never approach, maybe we'll approach in 50 years or 200 years, etc. So just I wanted to give you the next horizon. Quantum mechanics is about Planck scale in the sense of the Planck constant and 10 minus 8, 10 minus 10 meters and energy about electrovolts, 10 minus 19 joules. When we will approach 10, 9 joules per microparticles, we will be at the new horizon, then we will be challenged by some new physics, and it's called new physics. So I'm happy that I remind, but sorry that I extend for 2 minutes more, and I will be more than happy to answer if there are questions now or during the day, and tomorrow I will be also very happy to talk to you. So please don't be shy at that point, ask and let's continue to communicate. And it's a very old book. I have the translation in Serbia. It's a Berkeley course on quantum physics, but I still propose to find in English, or if translated in your native language, there are also very good ideas how to understand quantum mechanics for the very basic concepts, as I try to do here. Thanks a lot.
Everything was clear. You said that maybe we will never reach this level, but taking this opportunity, I would like to say that Einstein, when he proposed gravitational waves, he said that there is no way anybody to experimentally measure that. So it took about 100 years till LIGO detector detects gravitational waves, about 10 years ago. In fact, one of the persons who invented the technique to measure to such a small scale in order to see gravitational waves, Professor Weiss from MIT, died at the age of 92 last Monday. And there is a video, I will try to present it at the end of the morning session, where he says that he wanted to see the face of Einstein reading the paper that they had published back in 2011, managing to measure to such small dimensions. So thank you so much, Professor. It's always a great pleasure to have you with us.
Thank you so for this. But here there is a small, small nuance, small difference. This is about Gedenken experiment. So it's not possible at the moment to think about how to even create as an idea experiment beyond the Planck scale. But of course I agree with you. We have to be optimistic, and we have a lot of things from the history of science that optimism is well based. So I agree with you, but just I said it's a different type of experiment that Einstein have in mind. Yes, please.
Thank you so much. So the next presentation, it will take us to the sun. And the aim of the presentation is to demonstrate how important quantum mechanics is in our life, not on our everyday activities, but to our life, because sun is the source of the life on our planet. So we have to see how quantum mechanics are entering in this process. So Eleftheria Sotiriou from the National and Kapodstrian University of Athens. Her field of expertise is solar physics, and she's going to present to us the quantum phenomena that are taking place to this unique laboratory, unique quantum let's say, laboratory, this unique reactor that we have in the center of our planetary system. Eleftheria, you have the floor. Just to make a change here, and just to take this one.
Okay, so hello everyone. My name is Eleftheria Sotiriou and I'm a student at the National and Kapodstrian University of Athens. Thank you for having me here today, and as mentioned before, today we will talk about, well, basically why the sun is shining. So, let me try, okay. Here is a short structure, let's say, of my presentation. So in the beginning, we will start by explaining some of the characteristics, basic characteristics of the sun. And then we will talk about the energy production in the sun, and then how this energy is transferred in outer layers. And at the end, we will shortly speak about the journey of discovery around the sun and how, yes. Okay, so here are some basic characteristics. The diameter of the sun, which is 109 times the diameter of the Earth, and its mass is about 333,000 times the mass of the Earth. Well, the sun's age is right now currently 4.6 billion years. And the sun is supposed to live for another about 5 billion years. We'll talk about this after. As most of you know, probably the light takes light 8 minutes to reach us from the sun. So if we see something right now, for example, an eruption or something, it would have happened 8 minutes ago. And the last thing from this slide is about the sun's rotation, which is different from Earth's rotation because the sun is not solid. So that's why it has a differential rotation, which means that it takes longer to rotate around the poles than for the plasma to rotate around the equator. Just some important information about the anatomy of the sun. So in the center we have the core, followed by the radiative zone, and then we have the convective zone. Afterwards there's the photosphere, which is the surface of the sun, and then we also have the chromosphere and the corona, which follows. So here you can see basically the ways of life, let's say, of different stars. Our sun is somewhere there, so it's a yellow dwarf right now. And it's supposed to become a red giant and then end up dying as a white dwarf. This is the life specifically of the sun. So right now you can see where we are at 4.6 billion years. And in a couple of billion years more, it will start growing. The sun will start growing and become a red giant, and then start to become a white dwarf. This here is a Hertzberg-Russell diagram, HR diagram, which basically involves all the stars in the universe. This big line that covers basically the whole diagram is the main sequence, and you can see our sun is right there in the main sequence. So this means that it's in the main part of its life, and this is why it basically burns hydrogen into helium. So how does this burning work? We say that it burns hydrogen into helium. So here we have hydrogen and we have helium. As most of you probably already know, hydrogen is just one proton, and it which has around it one electron. But inside of the sun, maybe that's weird, inside of the sun, there are that high temperatures that the proton can't hold the electron anymore. So when we say hydrogen in the core of the sun, we just mean the nucleus, which is a proton. Same goes for helium, we just have the nucleus in the inside of the sun. Okay. Yes. So in nuclear physics, there are two basic, let's say, interactions, fission and fusion. In fission, we have basically large atomic nucleus, which actually breaks into smaller particles. And in fusion, we have lighter atomic nuclei that afterwards form a heavier nucleus. So knowing that we are starting from hydrogen and ending up with helium, which is the one that you believe is happening in the sun? Yes? Perfect. So we have fusion because hydrogen is lighter than helium. Because of the large mass of the sun, its gravity actually pressures the core very much, which allows, let's say, the ideal circumstances, most of the ideal circumstances of fusion because of this large pressure. But in order for the fusion to happen, we need 4, let's say. Here we just have 2, it's a simpler example because we'll see. We need 4 hydrogen nuclei that will form one helium nucleus. But from what we know, we can't really have two protons approaching each other because of electric field and their repulsion. So how will those two end up colliding and creating something else? Usually, if the temperature was very, very high and ideal for fusion, we would have those, all of the particles inside of the sun, because of the higher temperature, would have a higher kinetic energy, and they would move that fast that they would overcome this barrier of the electric field. But the temperature, as we talked about, is 15 million degrees Celsius, and that's not enough for fusion, for nuclear fusion. So there must be something else happening, because the sun is really shining, so fusion must be happening, but what we know till here is not the way. So in classical physics, in order to overcome a barrier, we should have the ideal energy that we can actually climb above the barrier. But here is where quantum mechanics in the sun shining comes in. And we can actually travel through this barrier in quantum mechanics. So here in this picture, you can basically see on your left, we have the wave functions of a particle inside, let's say, a box. This box is, a potential well, let's say, in quantum mechanics. It's finite, because if it was infinite and the potential was infinite, the particle could not exit the box, from what we also know in classical physics. When you have something inside a box, it couldn't be outside of the box. But now in quantum mechanics, because this is finite, the wave function on the right side, you can see the squared wave function, which gives us the probability to find the particle in its position. So you can see from those, from those green parts here that the probability is different than 0. So we can actually find the particle, there is a probability to find the particle outside of this box, overcoming this barrier. So you probably, whoever came to the boat tour 2 days ago probably remembers that the sea was not like that. It was a bit more wavy. And you probably had trouble walking on the boat. Am I right? Some trouble. Okay. So probably you were trying to walk, and you were trying to step here, but you were stepping a bit to the side or to the other side, because the boat was moving a bit like that when it was at least on the dock. So that's kind of, let's think about it as this box that we were talking about, seeing it on the dock. This is the boat that we used. And when stepping, because we were on the upper part, most of us, I think, when stepping, we could find ourselves inside the boat or even outside of it in some low probability cases. And that's exactly what happens with the particles, the protons in our case. So here again an example, classical mechanics, we climb above the barrier, quantum mechanics, we can go through the barrier. And the new picture is the last one. You can see that this is again the wave function here of the proton, which shows that, after the wave function, of the proton, there's a, let's say, wall here. This wall is a potential wall, which means that it's hard for the particle to get in. In classical mechanics, it wouldn't. But now we can see that there is actually a probability for this particle to cross this wall and end up on the other side, because again, the wave function is not 0, and it still is a wave. As you can probably see, yes, here, the altitude of this wave is bigger this time than this time. And this means that the probability of finding the particle on the left side of the wall is higher than finding it on the right side of the wall. This is by the altitude of the wave function. Again here, if we were in classical mechanics, we would have a wave, for example, approaching a wall, and then it will be reflected and continue its journey on the opposite side. In quantum mechanics, when we have this, again, potential wall, we will see that the wave function, this time, hits this wall, and the part of it actually can get through the wall and continue its journey. And again, you see that the altitude of this wave function on the other side is a lot shorter than the wave function that is reflected. So again, there is a lower probability to find the particle on the other side than on this side. But inside the sun, even though this probability is really low, there are about 10 in the power of 57 protons. So this probability becomes really big, and it is actually the reason that fusion happens. So this short probability becomes bigger because of the number of protons. This is the fusion that happens. You can see it starting with 4 protons, or hydrogen nuclei, and we are ending up with helium. But there's another problem. You can actually see that if we have the masses of the protons added on the one side, the starting mass, let's say, we end up with helium, which has a lower mass than the one that we started with. So where did the excess mass go? Yes? Perfect. It got transferred into energy, and this excess mass, basically, because of Einstein's equation of mass and energy, is actually becoming energy and transferred around the core of the sun. So we have this energy now inside the core. How does it go on the outside? Because we can't really see the inside. After the core follows the radiative zone, where this energy is transferred via radiation. But there is a specific radius in the sun where this radiative, let's say, zone stops, because it's no longer possible to transfer this energy via radiation. This is where the convective zone starts. And let's see why it's called convective. So closer to the sun, in this zone, hope this works, closer to the sun, as you can probably imagine, because it's closer to the core, the temperature of the plasma is higher. And in the upper layer of this zone, the temperature of the plasma is not that high. And as we even know from here on Earth and gases and everything, the higher part of something will start traveling on top. So this is how convective cells, let's say, are created, and the plasma is going up and down in order to be heated, and down to be heated, and up so that the other plasma goes down to be heated. And this is how the convective zone works. And it's called convective because of the convection and convective cells. Sorry. So afterwards, follows the photosphere, which is the surface of the sun. It's what we can see. And then, as we said, we have the chromosphere and corona. But on the surface of the sun, there are some extra, let's say, events taking place. There on the surface we have sunspots and prominences. Basically, sunspots are darker regions on the sun's surface, and they are darker because of their lower temperature. And prominences are those, as you can see, loops up there that appear even when you see the sun from a coronagraph, if anyone has seen this before. We will show pictures after. This is the size of a prominence, let's say, and we've put Earth there to show the scale and how big this is. So this prominence is photographed by SDO, it's a Solar Dynamics Observatory, and it's taken in extreme UV. So depending on those sunspots and the number of sunspots that there is on the sun, each year, we can actually see that there is a pattern that the sun follows. There's a periodic, let's say, change every 11, as you can see here, years. So we're starting from 2010, and the sun is not that active, it's calmer, then becomes more active, and then returns to being calm 11 years later. Those are pictures, well, it's a collage, obviously, of the sun for every year of the 24th solar cycle. Here there's also a diagram to understand a bit more about the solar cycle. On the x-axis we have the number of sunspots during the years that passed. On the inside you can see 18, 19, those are the solar cycles. And we are now in, basically we've crossed the middle of solar cycle 25. And in pink you can see the prediction for the next years. So let's look a bit at those two arrows and what they show. So we can see at about 2014 and 2019 that 2014 is a maximum and 2019 is a minimum in solar activity and in number of sunspots, so solar activity. And you can see also here pictures of the sun in the solar minimum that we showed and in the solar maximum. Those are in UV and again in visible light so that you can see better the sunspots in 2014. Because of those sunspots, there are actually other outbursts of energy happening from the surface of the sun. Most important ones are solar flares and coronal mass ejections. So solar flares are basically outbursts of energy in the form of light. And this light travels in every direction, and as we talked about, it takes light 8 minutes to reach Earth. And then we have coronal mass ejections. This is a coronagraph, as we talked about, that hides the disk of the sun basically so that we can see the corona. And this is when coronal mass ejections happen, it's like they have like this loop form, as you can see here, because they are magnetic, they are basically plasma trapped around magnetic lines. And they travel and they also reach Earth sometimes in 1 to 3 days. This is a picture to see the difference. Here is a solar flare, no loop structure, and up there is a coronal mass ejection which has a loop structure. There are many satellites that were sent to space in order to observe the sun and study the sun. Some of them are here. You can see Parker Solar Probe in the first picture, which is the satellite that reached the closest, let's say, distance from the sun less than a year ago. There is SDO up there that we showed pictures that it took before, SOHO, and you can actually find data that those satellites got on the internet, on their websites, or for example for Soho in theater and stuff like that, where you can also see pictures and videos of the sun even right now. Yes, so even though there are so many missions that give us data depending on the sun and help us study the sun, none of them obviously can see its core. We can't see on the inside. So how can we be sure that fusion is actually happening other than seeing that the sun shines? We haven't seen on the inside. So this is the chain reaction that we showed before. And I want you to try and look at it and see if there's something that we could detect that could only come from this and not from somewhere else. Yes? Perfect. Electron neutrinos that are coming from the sun are basically how we got to see that fusion is really happening. So the fusion theory was firstly proposed by Eddington in the 1920s. And some years after that, Bethe showed his framework, which it's a more detailed framework, which got the Nobel Prize in 1967. And this was the standard model that he proposed. You can see here we have a part, let's say, of the chain reaction that we showed before with probabilities and everything. But yes, so we had the neutrinos. And then the Davis experiment started counting those neutrinos. And there was another problem, of course. So we were only able to detect 1/3 of the neutrinos that were supposed to come from the sun. And then scientists didn't really know what went wrong. Was it, they said that it was really difficult to count neutrinos, or they were maybe there was a mistake made there. So why was it that we saw only 1/3 of the neutrinos that we expected to see? What happened to the rest of them? Okay, so the thing is that every neutrino, there are 3 flavors of neutrinos, as you probably heard in previous lectures here. And there are electron neutrinos, tau neutrinos, and there are muon neutrinos. So here, what types of electrons were those coming from the fusion? Did I say electrons? What type of neutrinos? They were electron neutrinos. Perfect. So every neutrino, basically, it was proposed afterwards by Pontecorvo. Inside of it, basically, has a probability to change its flavor and become a different type of neutrino on the way. This has to do basically with the mass difference of the starting neutrino and the neutrino that it will become afterwards. And also L here. L here is the distance that it will cover till it changes. So it has to do with those and the energy. So its electron neutrino starting from the sun could change its flavor and become a muon neutrino or a tau neutrino. And this Davis experiment that we talked about was only counting electron neutrinos. So the other 2/3, basically changed their flavor on the way, and that's why they were not counted. I mentioned before that we couldn't really see the inside of the sun with all those missions. But the key to seeing the inside of the sun, seeing because we can never actually see, but the key to seeing it is not going the closest possible distance from the sun. It's going on the inside of the Earth, because this is where we can detect neutrinos. And this is a picture, let's say, of the inside of the sun that was created by the detection of cosmic neutrinos, and also got half a Nobel Prize in 2002. So yes, we talked about fusion in the sun, and this is how the sun gets its energy. How do we get it? How do we get energy? We have fuel, we have a lot of stuff, and we usually talk about how fuel and everything will probably end at some point. And the sun has actually, maybe, potentially, we don't know, a solution for this. And in Europe, there are efforts, let's say, to create such a fusion, and even bigger, let's say, than that's happening in the sun here on Earth, so that we can get energy from this fusion and use it for electricity and for anything that we need power and energy for. So this is ITER. It's a construction right now in the south of France, and we talked about how the sun has 15 million degrees Celsius temperature inside the core, and they're trying to reach 150, they're hoping to reach 150 million degrees Celsius, so it's 10 times more than the sun, so that you can imagine the energy coming from that. And yeah, this is for the future, and this was mostly it. So thank you for your attention. And yeah, I'll be here if you have questions or anything to answer. Yes. Well, maybe it's during eruptions, which have higher temperature than normal corona areas. So I guess it's that. And it's the upper limit of the temperature, so yes. Any other questions? No? Okay. So yeah, if anything comes up, I'll be here too afterwards, so, and also in the evening, so we can talk about it then. Thanks again.
Thank you so much. We will continue, let's say, the exploration of the applications of quantum mechanics. Our next speaker is Greek, but he's coming from the States. He is a student at Princeton University. He has a very big interest in theoretical physics, and he's going to give us a talk about the quantum applications in medicine. Spiros Terlemes has the floor. Oh, okay. We will need 5 minutes to connect his device, so we can have a small break if you want. We are very well in time in any case, so we can have 5 minutes. Break.
Okay. Hello, everybody. My name is Spiros. I'm a student at Princeton University. I'm a senior student at Princeton University. I study physics. I'm actually okay. So I'm probably going to use the mic. Can you hear me? Okay, so this is better. I'm 21 years old. I study physics, theoretical physics specifically, and mathematics at Princeton University in the States. And I'm going to be talking to you today about quantum physics and its applications to medicine specifically. You know, it's great to see you guys here, you know, talented people with goals and dreams and everything. It's really amazing because it reminds me of myself. You know, I used to be in your shoes, and it's really nice to see, you know, some young blood, even though I'm not so old, but still, you know, I'm really happy to be here. And I want to thank the AF, the Hellenic Association, for inviting me here, so thank you very much. Yeah, I think it's going to be a really interesting topic because a lot of times quantum physics is taught as a purely theoretical subject, and it is because, you know, it was initiated and discovered by theoretical physics, but has a lot of applications, and specifically the applications in medicine are sometimes not known to the public. So I'm going to talk today about 3 things, specifically the magnetic resonance imaging, the optical coherence tomography, and some more uses of quantum mechanics in medicine. And at the same time, at the end of the lecture, I'm going to talk for about 10 minutes about a surprise topic. I think you're all going to find that really interesting and definitely useful, or I think so. Okay, so what is MRI? I guess you've all seen this weird machine, or you've probably, you know, taken an MRI examination, but MRIs are really amazing diagnostic machines that have saved millions of lives, and they're literally based on quantum mechanics. So what they do, you go in the machine basically, the physician takes takes probably 10, 15 minutes, it depends on the MRI, and you go out and then the physician has a picture of your body. Basically you can see, your organs, your joints, your muscles, your soft tissues. And the way he does that is by using magnets. So you can see on the left side is a machine, and the right side is what you see using what I'm going to describe now as the NMR process. So what is NMR? NMR is basically the same as MRIs, as magnetic resonance imaging, but since MRIs are their purpose is for the general public, they don't want to use NMR, which is called nuclear magnetic resonance, because anything that has a name nuclear is kind of scary. But it's basically the same process. So what is NMR? Well, I guess you all know that when you have an atom, the atom has a nucleus, and around the nucleus you have electrons floating basically. And the nucleus is made out of protons and made out of neutrons. Now, in the simple case that you have a hydrogen atom, it's like the simplest atom in the world, the first element in the periodic table, the nucleus is made out of one proton. Now, that one proton turns out, and I'm going to describe how and why, turns out to be a magnet. So all particles basically behave like magnets. Now, your body is made out of a lot of atoms. And since every atom is a magnet, as I just said, it can interact with magnetic fields. That means that when you place your body in the MRI machine, that is basically a very large magnet, the atoms in your body interact with the magnetic field. Now, that interaction, I'm going to describe that in a bit, gives you very important information about your diseases, your physiological anatomy, and all those cases, and it's really, really important. So NMR basically makes use of the interaction of atoms and magnetic fields. And what happens is that you put an atom in a magnetic field, a changing magnetic field, and that changing magnetic field has a sort of like different spectrum of frequencies. So you have magnetic fields that change at a different rhythm. And for specific rhythms, you see different signals. Now, you can see on the right side that for some cases, you get those spikes. And those spikes is what we call resonance. So for different rhythms of the magnetic field, you get different resonances, so very strong signals. So when you get an NMR process and you sort of see those signals, you have what we call resonance. And that gives us really important information about the material that we're studying. So I want to go back to what I said before about particles basically being magnets. And it's really important and really interesting to think about that basically you get some like small spheres, if you want to call it particles. And those particles have magnetic properties, right? In our everyday lives, we see magnets as macroscopic objects, and you kind of like, it's hard for me at least to visualize how those macroscopic objects can generalize to small particles that have the same properties. And it turns out that the core behind the magnetic properties of particles is that they have what we call spin. So I'm not sure if you guys know what angular momentum is, but spin can be described quite easily. When you get a tennis, let's say they have a tennis ball, right, or a basketball or something, that rotates. And the way that it rotates around itself, right, like this or like this, is what we call spin. So spin is kind of the self-rotation of a ball. Now, when something rotates, it creates a magnetic field. It's the same thing as having a wire with current, right? So when current flows around the wire, it creates a magnetic field. That has been known for, hundreds of years, I guess 200 years or something. So it's sort of the same thing. When you have a particle that rotates around itself, it creates a magnetic field. But there's one very subtle, but at the same time fundamental difference, that protons are spin 1/2 particles. That means that they only have two ways they can rotate. They can either rotate this way or that way with a specific speed. Now this is weird, right? If you have a tennis ball, You can choose the tennis ball to not rotate, like stay stable, or rotate with a very large speed, or not rotate with a very large speed. You get those infinite options. But for protons and electrons, for that matter, you only have two options. It either spins this way or that way. Your electron cannot be stable. It's crazy that your electron cannot stay still. It's pretty insane, but that's what quantum mechanics tells us. Anyways, so because you get those particles that rotate, they behave like magnets. And those magnets can either point up or down. Now, what happens when you put those particles basically in a magnetic field, an external magnetic field? What happens is, as you can see on the left picture, if your particle has spin up, so it's an up magnet, it basically lowers the energy. So it goes on the lower side of the energy. It's a very stable state. If it has down spin, it's an unstable state with really high energy. So think of this as, think of my phone as being a magnet placed in a magnetic field, right? It can be oriented in many ways, but it's going to be stable only this way or that way. So it's sort of the same thing with those particles, right? They choose to orient themselves either this way or that way. This way is more stable, right? It has low energy, but this state is not really stable. It has high energy. So if I tilt it a little bit, it's actually going to drop down and orient itself to the lower state. Now, on the right picture, you see, well, on the left part of the right picture, you see a collection of particles, protons specifically, that are kind of like random, right? They're not oriented. They spin at different directions. You know, they're not correlated. They're just like doing random motion. And then suddenly you place a magnetic field. And what happens? Those protons orient either up or down, right? It's what I said before. So when you place a material with a lot of protons in a magnetic field, you get an orientation that's either up or down. What's really interesting about the right picture is that there are 5 particles, and 3 of them have spin up, but only 2 have spin down. Now, this is not random. There's a reason why more particles choose to have spin up and less particles choose to have spin down. And the reason is that, as I said on the left picture, particles with spin up have lower energy. And you know that nature is stingy, right? It doesn't want to consume a lot of energy. And therefore, it chooses to lower the energy for most particles. It's, you know, if you ever, learn thermodynamics, that's pretty obvious. But what happens is basically that if more particles have low energy, then the total energy is less. So, energy is not going to change. As I said before, nature is stingy. So it chooses more particles have spin up than spin down. Now, what happens if we have this collection here, the right one, the one that we have here, and we send E&M pulses, so electromagnetic pulses? It's really interesting that this basic idea is basically, dates back to 1905, I don't remember when Einstein got his photoelectric effect Nobel Prize, but it's basically a photoelectric effect. So when you have this structure here and you send electromagnetic pulses, they are basically photons. So the light that you see here is an electromagnetic pulse that is made out of photons, right? This is quantum mechanics. Now those photons have the ability to cause emission or absorption, right? So you can have 2 states, spin up or spin down, and when an electromagnetic pulse comes, it causes what we call stimulated emission. So the particle in the up state, the high energy, goes down to low energy. And as it does that, to conserve energy, it releases a photon, right? This is the very reason why we see fire. When you burn something, you have chemical reactions that, place atoms in high energy, and then they go down to low energy through a process called emission, spontaneous emission. But as they go down, they release photons. And then your eyes detect those photons, and that's why you see fire. So the same thing happens when you send E&M pulses in this structure here. They cause particles to go from spin down to spin up. So from high energy to low energy. And as they do that, they release photons. You might think that those photons are visible. They're not visible because the E&M pulses that we use are radio frequencies. And you know that radio frequencies cannot be detected by our eyes. They're low frequency for our eyes, which are basically sensors. But we can detect those photons actually through our NMR machines or detectors, and they give us really important information about the material that we're examining. Because the probability of detecting those photons is related to the structure of the material. So for different materials and different frequencies of E&M pulses, we get different photons, different signals. And then by analyzing those signals, we can learn really important information about the material we're examining. So now going back to the application of NMR, the process that I said before, to MRI, you place a patient in an MRI machine, and you apply a really strong magnetic field. So because the patient has a lot of water in its body, basically, and water is made out of hydrogen and oxygen, but hydrogen, as I said before, has protons. Those protons interact with the magnetic field. They get aligned, so either up or down, and then you send electromagnetic pulses. So they cause a photon release. And this photon release is detected and tells you a lot of important information about your patient. So it tells you whether your patient has, well, number one, you can construct images of joints and muscles and soft tissues, and everything is what you see on the right side, and that's just by analyzing those photons. And using that, you can detect, tumors and inflammation and anomalies, and it's a really amazing tool. It's an extremely important technology that is possible purely because it uses quantum mechanics. This whole thing of going from a high energy to a low energy and emitting a photon is only possible in quantum mechanics. You can't have that in classical mechanics. So some interesting facts about MRI is that there's probably 100 to 150 million MRI scans every single year. This is an insane number. It's pretty crazy. Unlike X-rays, MRI uses non-ionizing radiation. So what is ionizing radiation? When you have an atom and you send X-rays, what X-rays basically do is they kick the electrons of the atom to the outer world, right? So they destroy the atoms, basically. But MRI does not do that. It doesn't really kick the electrons out of the atoms. No, so it's safe in that sense because it does not really destroy your tissue. It doesn't really cause any genetic, mutations or any genetic destruction. So it's pretty safe, always in accordance with your physician, but in terms of radiation, you can get 10 MRIs a day, and you're probably not going to have a problem, radiation-wise. Also, what's really interesting here is that the magnetic field of an MRI is approximately 60,000 times stronger than the magnetic field of the Earth. If you sort of think about that, you have an entire planet. It's huge. And its magnetic field is really, really weak, that a single MRI machine is 60,000 times stronger. How crazy is that? Pretty crazy. Let me tell you something else that's kind of related to how weak the magnetic field of the Earth is, that when you have magnets on your fridge, they're basically able to resist gravity and magnetic attraction. Simple magnets in a fridge are stronger than the entire, attraction of the Earth, right? Because they stay on the fridge and do not fall down. So the Earth's magnetic field, as well as the Earth's gravitational field, are pretty weak in terms of, other forces like electromagnetic forces. Okay, so this was the MRI that's based purely on quantum mechanics, and I want you to appreciate how beautiful that is, and that, you know, literally quantum mechanics saves lives. It has saved millions of lives through its, you know, scanning processes. Okay. Now, the next thing I'm going to talk to you about is something you've probably not heard of. It's not that common because they use that for eye examinations, and it's pretty expensive. But it's very useful, and it's a technology that's going to keep improving, and we're going to see a lot of new results in the following years. And it's called OCT, optical coherence tomography. It's a non-invasive, painless procedure. So basically, you just, you know, you can see the lady there, you just sit in front of a machine, it takes a picture of your eyes in the way that I'm going to describe now, and then you use that to analyze your eyes and, you know, any problems that your eyes, or not just your eyes, other things as well, as we're going to see, have. And it uses interferometry. It's basically an interferometer. I guess you guys have heard of interference, right? No? Yeah? Okay, yeah. So here's the basic idea. This is a picture of the eye. By the way, I know nothing about, you know, the eye anatomy. I just know basic things, what's like the optic nerve and the retina. So I'm not gonna, you know, I'm not gonna behave as an expert here. So what I want you to see here is just the retina here and the optic nerve. So when we get an OCT, we want to examine those two parts, the retina and the optic nerve. And the way we do that is by sending electromagnetic waves again. It's basically the same thing as an ultrasound, but it behaves, instead of like sound, it uses light. And you know that light is pretty fast. It travels with 300,000 kilometers per second, right? So it's really, really fast. And you cannot use that to detect any time differences between the arrival of signals and, you know, the emission of signals. So it's really fast and doesn't really give you any information by measuring time differences. So it's not the same as ultrasounds that, you know, basically when you get an ultrasound, you send a signal, a sound, it hits some part of your body, gets reflected, and then you measure the time difference between the signal that you send and the time that it got reflected, and then that gives you important information about the body. But you can't do the same thing with OCT because light is really fast. But people thought of a really smart way of detecting the reflected light and actually getting important information about the body, specifically the eye. So here's a depiction of how OCT works. Let me explain. Here's a light source, the signal that you send, basically, and here's a beam splitter. So what it does, it just splits the beams into one going up and one going this way. Now the beam going up hits a reference mirror, so it's reflected back. And the beam going through hits the eye. This is the eye right here, the depth of the eye, specifically the retina and the optic nerve. And depending on the depth of the optic nerve, depending on the depth of the eye, you get a reflection back that is a function of the depth and any depth anomalies that might appear there. Now, when those two signals, one coming here and the other one coming here, interfere, so you have two waves and the two waves interact, so that's what we call interference, and are basically moved to the detector, and then you detect the interference pattern, you could construct an image of the depth of the eye. Now, what happens is that the path length, this path length here, is directly involved to whether you're going to get an interference pattern or no. So for really small depths or, you know, whatever anomalies you might have, you will get, in your detector here, interference patterns that tell you whether your depth is, you know, large or whether you have some sort of like deficiencies in your eyes just by detecting the signals. So this way, you do not have to measure time difference. The only thing you have to measure is interference patterns. And that's pretty easy to do, right? Because you just, how do you measure interference patterns? You just have detectors that detect the photons that appear, think of the double slit experiment, right? It's the same thing. You send electromagnetic waves that go through two slits, and then you detect the interference pattern, right? So you just measure photons. So it's the same thing as here. You measure photons. You don't really measure time as you do for ultrasound. So the result of that is that you get a depth profile of your tissue, layer by layer, right? Because for different depths, you get different detections. And then again, you do that for different frequencies and different depths, and you get a 3D image basically of the eye. You can see on the right side here what a physician observes when he tries to diagnose a certain patient with an eye problem. But what's really interesting about OCT is that it gives you more information about your entire health, not just about your eye health. You can use OCT to detect cardiological, dermatological, neurological diseases, and many more. So it's pretty interesting that your eyes actually contain so much information about your overall health. Again, there's a lot of research and money invested in the business of, ophthalmology, and it's really, really interesting. In the next years, there's going to be a lot of new applications and breakthroughs. And now there's some, I know this is kind of irrelevant, but I thought it was pretty interesting to share with you. So I'm not sure if you've heard Elon Musk's Neuralink, but what he's basically trying to do as a side project is to enhance our vision so that we're going to be able to see higher and lower frequencies. Right now, what we see as color, as light, is a very small range of the entire light spectrum, of the entire electromagnetic spectrum. It ranges from 400 nanometers to 700, something like that. But we cannot really see UV light or infrared light. However, what he's trying to do, I'm not sure if it's possible or no, there's a lot of details about that, is to enhance our ability to see higher and lower frequencies. And if that's achieved, you would be able to see right now, your phone's basically emitting radiation. If you could see basically radio frequencies, which is pretty crazy, right? You would see literally the radiation of your phone as a color. I don't know, but that sounds crazy. Anyways, back to OCT. OCT has preserved sight to millions of people. So again, physics literally saves lives. And I think it's a very, very important application and a great use of interferometry. And let me talk now about some more uses of quantum mechanics in medicine. I thought of talking about PET and going into detail because it's really amazing, right? It's again pure quantum mechanics, but not the first stage of quantum mechanics. It uses sort of the second revolution of quantum mechanics with quantum field theory and antiparticles and all those things. So what it does is that it uses a certain technology to measure positrons. So what is a positron? It's basically an electron with an opposite charge, right? It has the same properties as an electron, sort of, but with an opposite charge. And it has the ability to annihilate charges, annihilate electrons. So when you have an electron and a positron, and they meet, they annihilate each other, but they also energy needs to be conserved, right? So they produce gamma rays. And when you detect those gamma rays, you can get a 3D map of your tissue activity. So you send positrons, you inject radioactive material basically that makes the interactions between positrons and electrons possible. And then you detect basically your positrons and your electrons, and you get really important information about your tissue. The next thing is X-rays and CTs. And again, you've all probably heard of X-rays and CTs. They just make use of the photoelectric effect. Is again, just ionization of atoms and photons and Compton scattering and all those things. So in its very basis, X-rays and CTs are again based on quantum mechanics. You wouldn't have been able to get an X-ray without quantum mechanics. And the third part that I want to talk about is a bit of a more general statement that chemistry as you know it is almost entirely based on quantum mechanics. So you study chemistry, you study molecules, you study, ions and the periodic table and and chain reactions and whatever. And the periodic table, for example, can be almost entirely deduced from Schrödinger's equation from quantum mechanics. It's really beautiful that you have a theory that not only tells you how the world works fundamentally, but it also explains the entire chemistry of our planet, basically. And chemistry is the basis of all drugs, right? Drugs use chemistry, and they make predictions about how, certain molecules are going to interact with other molecules, and, how your DNA or whatever is going to be changed. And those drugs use chemistry and therefore use quantum physics. So, in a sense, medicine and the pharmaceutical, science field is, again, based on quantum mechanics. Now, you can say that about most things. Since most things are based on chemistry, then, most things are based on quantum mechanics. And this is true. If we didn't have a theory of quantum mechanics, we would not have a theory of, condensed matter physics or, solid state physics. And solid state physics gives you the ability to produce things, right? You have all your chairs and computers and everything, and that's based on quantum mechanics because, you learn a way to manipulate materials and build new materials based on quantum mechanics. So it's more than just a simple theoretical and mathematical concept. Quantum mechanics is the essence of our everyday world and how particles work in a very fundamental way. There's huge problems from quantum mechanics, the interpretation of quantum mechanics, but it's still fascinating that even though we do not really understand how quantum mechanics works, we're able to use it in a very amazing and advanced way. Okay, so these were the things that I wanted to talk to you about in terms of quantum mechanics and medicine. Do you guys have any questions before I move to the next part? Yeah, sure.
Okay, so at some point you mentioned PET scans and that they use positrons.
Right.
But as far as I know, antimatter in general, when it comes into contact with matter, it gets destroyed. So how are these positrons stored and contained so that they can be used?
Right, that's a good question that I do not know the answer of because I have not really studied PET in detail, but I don't think it's that hard because if you have radioactive material, you can sort of use that to produce positrons, I guess. But I don't want to say something I don't know about. But essentially, I don't think they need that many positrons because you sort of want to see the interaction of positrons with electrons and the release of gamma rays. And I don't think you need that many gamma rays to sort of like get the basic structure of the material. But yeah, I think they just use radioactive material and then kind of like manipulate that in a certain way to produce positrons. But that's all I know. Good question though. I'm sure they can find a way to use positrons. I mean, they do all those experiments and, so many things by using positrons and other antimatter particles. So I guess they just find a way to find those particles. But yeah, good question. Yeah. Sure.
Okay. I wanted to ask about the MRI contrast agent that we inject, that is injected to the patients during the MRI. It helps to the magnetic field. It clears the view. What does it do exactly?
Right. So you get a clear. Okay. So depending on the material that you have, so different materials behave different ways when they're when magnetic field is applied. Right. So you use those things to get a more clear structure of the signals and the resonance that you detect. So what happens is that you place you place a proton, so let's think of a proton, right? You place that in a magnetic field. If the magnetic field is really strong, most of them are aligned either up or down. Then you send E and M pulses, so it's basically a rotating magnetic field. That rotating magnetic field causes those protons to go down to a certain state. You don't really measure the signal, you measure the time difference, the relaxation time as we call, and that relaxation time really depends on the material that you use. So for different materials, your relaxation times are different. And you basically have 3 types of relaxation times, and that's what you measure when you use an MRI. And when you inject that kind of like material, it helps measure those relaxation times in a more accurate way, and therefore get a picture that's more accurate.
Okay, thanks.
Right. Okay. Okay. So I hope this was interesting enough. I don't want you to kind of like learn everything that I said here. It's not that important. Just, get the basic idea of the applications of quantum mechanics. And I'm going to talk about something that I think is really important. Like, if you're going to hear anything today and actually, remember something, I think this should be it. So if you want to pay attention, that'd be great. So I want to talk about some things I've learned, through my interaction with my classmates, my professors, like award-winning professors. So I'm not really saying those things on my own. There are things that I've talked with really smart people. And I've also talked about those things with my friends, and I've kind of like realized some things that I think they're really fascinating to share with you. And the first thing that I want to talk to you about is that physics is literally so much fun. I'm not sure if you guys enjoy doing physics. I guess you're here because you like physics, and that's great. And I hope you keep liking physics, but at some point, you probably want to go and study physics at a university, a really prestigious university or something, and you're going to go down a path of having a lot of homework, a lot of work, having a lot of pressure from your professors, from your fellow students, from the academic industry, because in a sense it's really an industry, and that might drain away your fascination about physics and your joy for physics, and that's a really sad thing to see to basically see happening. I see that at Princeton as well. A lot of smart people who came to Princeton and were really happy about physics, and after a year or two they're just like, okay, I'm doing physics because I have to, but I don't really enjoy solving 20 problems a week that do not really, teach me anything. And my advice to you, it's not really an advice, it's just from my personal experience, is to not stop having fun doing physics. That's the essence for why we do science, for our own curiosity, answering our own questions and having fun. And, a lot of times your environment is going to affect you and make it harder for you to have fun. But if you always have fun doing physics, then you're never going to think about, like, this kid got his PhD when he was 20 years old, why do I even bother doing physics? Or am I behind? Or how many things have I learned? Or, like chasing time. You don't need to chase time. Enjoy physics. And because, you might think that I'm saying those things, from my personal experience, I want to share with you something that you might not know. It's a quote from Feynman, and he said, "Physics disgusts me a little bit now, but I used to enjoy doing physics. Why did I enjoy it? I used to play with it. I used to do whatever I felt like doing. It did not have to do with whether it was important for the development of nuclear physics, but whether it was interesting and amusing for me to play with. Now that I'm burned out and I'm going to never accomplish anything, I'm going to play with physics whenever I want to without worrying about any importance whatsoever." So we have Feynman here saying that he's never going to accomplish anything. The same guy that, a few years later got his Nobel Prize. So, it's really a process of liking physics and not liking physics and liking physics. And, a lot of people go through that process, but you got to stay all the way and not get discouraged. So if you want to, sort of like keep something from today, that's lesson 1. Then lesson 2, that, you're kind of like young. I'm not that much older than you, but I realize that with time, as I said before, you're all gonna You have your dreams right now about physics and your career dreams and everything, but you should never forget the importance of human relationships, and that if you want to be a really successful scientist, you can't do that by yourself. Like, you can't just be isolated and do physics or math all day and, not think about anything else. You can do that for a short time, but you're going to get burned out. And that burnout can be really heavy. I've met people who were, really promising in their fields, 20, 25-year-olds, and at some point they just said, I cannot do this anymore, I can't take the pressure, and just quit. And in those times, what you need is some sort of anchor, some sort of stability, and that's offered by human relationships. Your friends, your boyfriends, your family, your girlfriends, whatever, just never forget that, because at the end of the day, we're all human, and we're not really, just machines doing physics. And now that I mentioned machines, my lesson number 3 is about our responsibility as prospective scientists, because, I'm not really a scientist anymore, not anymore yet, because I'm studying still, but at some point I'm going to be a scientist, and I'm going to play a role in some small field in my, in my research interests. But my small part can actually have a huge impact if it's used in a bad way. And we see a lot of scientists and a lot of specifically physicists and, computer scientists right now using their technology in really harmful ways, specifically with artificial intelligence. Artificial intelligence, in case you do not know, poses a huge existential risk for humanity. I'm not exaggerating here. I think, if you guys are interested, you should study about it. It's really, really important to learn and educate yourselves about the uses and the dangers of AI and AGI, artificial general intelligence. And that's what, companies are trying to build right now, AGI. And if AGI is successful, you guys are all going to be unemployed. I'm going to be unemployed. Everybody's going to be unemployed. You're not going to be able to do physics or anything. I mean, you're going to be able to do physics, but it's really not going to matter, because AGI will do that in a more efficient way than you will. And therefore, I think it's our responsibility to change this and use AI as a tool, not as a replacement for, human labor and science. And in a sense, it might be too much to say that, but, you guys are really smart people, really capable, and you are sort of the chosen ones to lead, this generation to kind of do things better than the previous generation. And there's not that much time. There's so much money invested in AI right now that is not safe whatsoever. There's probably millions of people working on AI, advancing in AI, and hundreds or I don't even think thousands of people working on AI safety. There's very little people working on AI safety. So if you guys want to work in, computer science or something, think of working on AI safety, advocating for regulations, doing things that are actually going to have an impact if you want to keep our world, as beautiful as it is. Because I hope you all appreciate this, this beautiful world here, and not this world that, is pretty possible actually in next years, next decade or something. Not maybe decade, but 2 decades. And another thing that as physicists you can have a huge impact is climate change. Climate change is here, you're seeing those things, and specifically in Greece, we're seeing this every year with wildfires and floods and all those things, and they're just going to keep getting more intense if we do not act, if we don't do anything. I'm not even sure that if we act now, we have a lot of, chances of solving the issue, but we can definitely delay the issue. And what we need is physicists, really smart people who are going to work on preventing those climate crises from, getting worse. Because we need our planet, and we need to have, to protect our planet. And at the same time, AI is using huge amounts of energy, both for, cooling its servers and a lot of potable water, that we in Greece as well are going to have, a lot of problem with potable water. There are some experts saying that Athens is not going to have water in 2027, that, our water resources are going to be drained away, and that's that's pretty urgent, right? So those are all questions that we need smart people to think about, physicists specifically, but always have your ethics in mind, right? Never just do something for your own curiosity without thinking about the implications. It's very important to think about that. You have a responsibility, and I think that's a collective mistake of academia, that it solely focuses on, a specific research topic. You have a responsibility as scientists, prospective scientists, and that's actually the really amazing role of science in our society. It's a democratic process that can have a huge impact if used correctly. So you should be really glad that you have the capabilities of serving that. Okay, enough talking. Oh, and also, if you guys have not watched Don't Look Up, it's on Netflix. It's a great movie. You should all watch that and kind of think about how that is related to what I said about AI and climate change. Okay, so thank you. This is my talk. And if you want to ask any questions or anything, I'm here.
Thank you so much. Numerous great messages for the students, and I think for all of us. So thank you, and I hope all the best with the continuation of your. Yes. Because he has asked for questions. Maybe the questions are only for the last part, for the three messages. Okay. So.
Okay. Yeah. Sure.
Hello.
Hi.
I wanted to ask you, what do you think we should do about AGI and beyond?
Okay. That's a great question. So, here's the thing. You cannot really slow down AGI right now. It's a natural evolution of science. It always progresses, right? And now that you have those trillions of dollars kind of like, flooding in, and all those huge companies, Google, AI, Meta, OpenAI, Meta, and all those companies sort of like investing in, AI, you can't really stop that. What you can do, and I believe that's the only way to sort of like, not solve, but maybe delay the AGI issue, is to collectively, as a field, academia and other fields, to push for regulation. It might not be successful, but that's the only way that you can sort of have an impact right now. The only one who can stop those companies or delay them or put regulations are the governments right now. I mean, that's undeniable. I'm not saying that they will do that. I'm not saying that they do not have other conflicts and other conflicting reasons why they are not going to do that, but they're the only ones who can stop that. Now, our role as scientists is not really related to governmental policies, so we do not really have an impact on that. So going back to your question, it's really hard to pinpoint down to exactly what we should do as, prospective scientists, but the important thing is that you're so smart and so talented that if you educate yourselves about those things, you're going to really think about ways to, place AI safety regulations. So I do not know the answer, but I definitely know that if millions of people work in advancing AI, and only 1,000 of them work in AI safety, we can definitely do much better if more people work in AI safety and think of ways that you can sort of like, place some safety nets for AI. That's number one. Number two, and it always helps, is to really advocate for AI. If I can have an impact on, 5 people, let's say that, out of the audience, only 5 of them are going to think that AI is really an existential crisis, and you have an impact on other 5 people, and they have an impact on other 5 people, that's going to keep increasing, right? So that's really important. Never stop advocating for AI and regulations and climate change because you do not really know where your impact is going to stop. So yeah, I don't really have a clear answer on how to place AGI regulations, but we just need more smart people to think about those very urgent things.
Thank you.
of course, Spiros, for us, for the Hellenic Physical Society, is, let's say, something like the best student. Spiros used to participate in all the national competitions of the Hellenic Physical Society, and as far as I can remember, you always won the first prize. And of course, he won a medal to the Balkan Physics Olympiad. So, Spiros. I would like to describe, let's say, your journey from your school in Komotini towards the Princeton. What was the route that you followed in order to get there? Right. Please, let's take the opportunity now to allow Spiros to describe all this journey towards Princeton. Right.
Okay, so I don't really like talking about myself, but I guess you're probably going to have some things to learn about, the process of applying to, universities in the United States, and I think that might be a great opportunity. So that's why I'm doing this. But so basically, I come from a really small town. It's called Komotini. It's only sort of like 60,000 people. Used to be underprivileged in comparison to Thessaloniki or Athens. But I think that actually might ended up being a good thing because you have sort of like not that many distractions and you can focus on your work. And that was kind of like an initial spark for my interest for physics. And so I kind of pursued that. I went to a lot of competitions. Initially, I wasn't that good. I mean, I was not winning, but I didn't really care about it because I enjoyed physics. And, I studied hard. I really enjoyed doing physics, and therefore it was not really studying hard for me, which is having fun, And I guess it might be the same thing for you. And then when I was a junior, in U.S. terms, I'm not, whatever, I was like in second class of high school. Senior high school, actually. I applied for scholarships for Princeton University and other places, and I got into Princeton because I had, kind of a solid CV. My distinctions were sort of okay, and I had a really good interest of, what I wanted to do, kind of like quite specific. I really wanted to work in theoretical physics and mathematics, and I sort of knew what I wanted to do, and I think that played a major part in getting accepted at Princeton. And then I went, I went to the United States, and it was kind of like hard. Not hard, it was kind of weird going from a small town to, one of the best universities in the world, if not the best one in physics. But it was an amazing journey, with a lot of, amazing people that I met through the way, and I keep meeting every day. Going to Princeton or other places is a huge opportunity. You get to meet people that you never really thought you would meet, and you can get, so many things and so many, you can really learn things about yourself through that process of interaction with, very smart people at Princeton and other places. And what's really good about it is that you get a lot of opportunities for physics, for kind of like evolving as a human being in other fields as well, other areas, not just physics, because you get the opportunity to go to classes about history, about philosophy, and all those things are actually very much needed because, as I said before, you can't just be solely a physicist that does not have any sort of like, interests in other fields. And it's your responsibility to have your ethics sort of like aligned with your work, and having knowledge of history and knowledge of philosophy and knowledge of, other areas is really useful for building that. Anyway, so that was my process. Now I'm a senior, so I have one more year left. Not sure if I'm gonna, I'm probably not gonna apply for a PhD next year. I'm probably gonna apply the year after that. But yeah, I don't know. If you want to do this, if you want to chase your opportunity in a great university in the United States or other parts of the world, I'm really happy to help if I can. I'm not sure if I can, but if you have any questions or anything, you can definitely email me. Well, you can find my email online, I'm sure, and ask me whatever. I'm always eager to really, help people, talented people. I like that. So yeah, I don't know what else to say, but yeah. Thank you.
Okay, Spiros, thank you very much. We may take advantage of Spiros for the next couple of hours. He's going to be with us for the lunch, so you may ask him whatever you want. Okay, this session has finished. Thank you very much. The lunch is going to be at 2 o'clock. Thank you.